Previously, we've discussed the Galilean coordinate transformation equations. In, in Galilean coordinate transformation, they relate the coordinates x, y, z, which is that is the point in a frame of reference S, that is the rest frame, to the coordinates x prime, y prime, z prime, and that is the point in the second frame, S prime frame. S prime frame is the moving frame, uh, moves at the speed, constant speed u. Okay. The second frame moves at the constant speed u relative to S frame in the positive direction along the common axis, that's x, y, x, and x prime axis. And the time scales of these two frames are the same. So the t prime, which is the time in the moving frame, is the same time scale, which is t, in S frame, the rest frame. The Galilean transformation equation is only good for speed, or it's only valid if the speed approaches to zero. If we're going to compare the speed of the moving frame to the speed of light, it's much less than. Okay? So let us discuss, in Galilean transformation equations, uh, the special theory of relativity is not utilized. There's no left attraction, there's no time dilation. Let us discuss the new another Lorentz another transformation equation, what we call the Lorentz transformation. And what is this Lorentz transformation? This is the mathematical method of relating quantities between inertial reference frames while utilizing the special theory of relativity, right? So unlike in Galilean transformation equation, uh, we don't deal with the time dilation since time scales between two frames are the same. The length construction, right? Since the frame or the moving frame is moving at constant speed u, and that u comparing the speed u to the speed of light, it is much less than. Right? So what is this? What are the Lorentz transformation equations? How is this differ from Galilean transformation equation? Suppose we have two inertial frames. We have S and S prime. So initially, these two frames are superimposed, so meaning the x-axis of S frame is along the x prime frame, okay? And then the y-axis is along y prime. Right? This is y prime. This is y prime. Okay, and the z-axis of S frame is along the z prime axis of z prime frame, and that is when t equals t prime and t equals 0, or t prime equals 0. Oh, initially these two frames are superimposed. Okay, so they have the same origin. So the coordinates, like in Galilean transformation, the coordinates found in S frame is x, y, z at the time t, and then the coordinates found in S prime frame, which is the moving frame, are x prime, y prime, and z prime at time t prime. Right. So we will let this expression y over square root of 1 minus u squared over c squared. Usually in relativity, this expression y over square root of 1 minus u squared over c squared is expressed in gamma. Okay, this is the Greek letter gamma. Okay, so gamma here equals 1 over the square root of 1 minus u squared over c squared. Now, if we're going to express this expression into gamma, then the time dilation time dilation uh, will be expressed into delta t equals the proper time times this expression gamma. And the length contraction will be L equals the proper length over gamma. Okay. And we will let the expression, um, the speed of the frame u over the speed of light c equals beta. Then the gamma will be expressed into gamma equals 1 over square root of 1 minus beta squared. Okay, again, beta is the ratio of speed of the frame, moving frame over the speed of light. Right. So S frame will move at the speed u, constant speed u, okay, to the right, and it is along the x-axis. Along x-axis with respect to stationary frame or S frame, and that is the S frame. So the distance from the origin of the S frame, the rest frame, to the origin of the moving frame is u prime, which is u prime, will be the distance moved by the S prime frame at a certain time t. Okay. Since speed v equals distance over time, and distance here is the speed t, speed times t. Since the moving frame moves at a speed u, then the distance moved at a certain time t will be ut, and that is the distance between two um, origins of the three axes, the xyz axis. The origin is o, and then the origin for x prime, z prime, and y prime axis is o prime. Okay. Now the distance x from O to P. P here is the event happening in the S prime relative to S prime. Okay, so the distance x from O, the O which is the origin of the S frame, to P. P here is the event observed by the observer in S frame. Okay. So, or seen in S frame will be x plus ut, which is the distance between two origins of two frames, plus x prime. What is this x prime? X prime is the distance of the event from the y prime axis. So as seen in Galilean coordinate transformation, we have x equals the speed of the frame, moving frame, plus the time t um, observed in rest frame, plus the distance of the event. The event here is point P, and point P, the distance from the y prime frame. But this frame, the moving frame, moves close to the speed of light, right? So we consider length contraction here. So instead of expressing it from x equals ut plus x prime, and that is for Galilean coordinate system, we will express x into ut plus x prime times the square root of 1 minus u squared. And what is this x prime square root of 1 minus u squared over c squared? This is the length contraction, right? The length contraction. It will only occur if the frame moves very fast, it is close to the speed of light. So we will solve for the x prime, okay? We're rearranging this equation. Then we have x prime equals x minus the speed of the moving frame times the t over the square root of 1 minus u squared over c squared. And this square root of 1 minus u squared over c squared is expressed in gamma. So x prime will be x prime equals the quantity of the x minus the speed of the moving frame, which is u times t, okay, times gamma. Now, what will be the length observed in S prime? if that length is perpendicular to the motion of the moving frame, which is the S prime frame. The length perpendicular to the relative motion are not affected by the motion. Okay, like when the length is perpendicular to the motion, direction of the motion is either positive direction or negative direction, then there's no length contraction. Okay, since y axis is parallel to the perpendicular, I mean perpendicular to the direction of the motion, as well as z is also perpendicular to the direction of the motion, then y is still equal to y prime and z is still equal to z prime. Alright. The principle of relativity that the form of transformation from S to S prime frame be identical to that form from S prime frame to S prime. But the only difference is the change of direction or sign of relative velocity component of the velocity u, which is the speed of the moving frame. So now if this is the moving frame, okay, what moving frame, let's say this spaceship, this is the moving frame, the spaceship, and the rest frame, let's say the earth, spaceship, and this is earth, the rest frame. Okay, now what is the observed direction of motion of, of the observer in rest frame is earth, will be at that direction. Okay? According to the observer in earth, spaceship moves along positive x-axis. That's the speed of moving frame, the S prime frame, relative to the observer here in S frame, the rest frame. Now, but what will be the observed speed, okay, or the observed direction of motion of the observer in the S prime frame, or the observer inside the spaceship, the moving spaceship? Now, if this is the spaceship, the moving frame, and this is the observer, Earth, okay? So what is the observed direction of motion of this Earth will be at that direction. Now, let's go back here. If u is the observed speed relative to S prime, that is the observed speed of the spaceship relative to S prime, okay, then the speed of Earth relative to S prime frame, or the relative to the observer here inside the spaceship, will also be u. That is the principle of relativity. Okay, the transformation from S prime to S prime frame will be identical to the transformation form from S prime frame to S frame. But the only difference here is the change of sign of relative velocity. So we can express the x instead of x prime, we'll express x into x prime. Okay, let's go back to that equation of x prime. X prime here is x minus ut times the gamma. Now, if you're going to have the equation for x, there is the change the direction of u. Here is negative u, then the expression for x will be x equals x prime plus ut times gamma, not anymore negative. Right? From this equation, let us solve for the t prime, or the time observed in the moving frame. So t prime, rearranging the equation, t prime equals x over the speed of the moving frame times gamma minus x prime over u. Okay, and what is this gamma? Because remember, gamma here is 1 over square root of 1 minus u squared over c squared. Okay, so we have x equals x times the square root of 1 minus u squared over c squared over u minus, what is this x prime? This x prime is what? X prime equals x minus ut times gamma. So let us substitute x prime by that expression. And what is this gamma again? That's 1 over square root of 1 minus u squared over c squared. Then x prime, so this is minus x minus ut over u times the square root of 1 minus u squared over c squared. And this 1 over square root of 1 minus u squared over c squared is the expression, is the gamma. Okay, so multiply, cross multiply. We're going to cross multiply here. So that will have the same, we can combine these two terms. They must have the same denominator. So t prime here equals x times, multiply this. This is raised to the power 1 half, and this is also raised to the power of 1 half. Then 1 half plus 1 half equals 1. Then we have x times 1 minus u squared over c squared minus x minus ut. Then combine these two. Then we have u times the square root of 1 minus u squared over c squared. And distribute x times 1, we have x, then x minus negative u squared over c squared, and we have negative x u squared over c squared. And this one, this is negative 1 here, we'll distribute negative 1 times x, then we have negative x, then negative 1 times positive negative ut, then we have positive ut. So we can cancel x here since that's x minus x. What is left is ut minus x minus u squared over c squared all over u square root of 1 minus u squared over c squared. We can divide each term by u, or multiply both numerator and denominator by 1 over u. 1 over u over 1 over u is just equal to 1, so we don't change the value of this expression. We can cancel u, so what is left here is t, or t prime equals t minus ux over c squared all over the square root of 1 minus u squared over c squared. Okay. Since gamma is 1 over square root of 1 minus u squared over c squared, then this is t prime equals gamma times 1 minus ux over c squared. Okay, that's for the t prime. Okay. So collecting all those transformation equations, the equations relating the time and position of the events as seen in rest frame or the S frame are t, it is the time observed in S frame, the rest frame will be t prime here is the proper time, plus the speed of the moving frame relative to S frame, x prime, okay, the distance of the event from y prime, y prime axis, over c squared times gamma, and x here is x prime plus the speed of moving frame u times t prime times gamma, and y is still y, or y prime is still y prime, and z prime is still z prime. Now for the equations relating the time and position of the events as seen in S prime, the moving frame, will be t prime equals t minus the speed of the moving frame times the x times c squared gamma, and x prime is x minus the speed of the moving frame times time. This time here is the time observed in S prime times gamma, and y prime is just y, and z prime is z. Okay. So that's for Lorentz transformation equation relating the time and position of the events as seen in two inertial reference frames, the S frame and the S prime frame.